This is Magic 063, Differentiable Manifolds. I'm Kirill Mackenzie, and this is the podcast about cotangent bundles. Start by thinking about what a tangent vector does to functions. So x sub m is a tangent vector at point little m, and it maps a smooth function to a real number that's the derivative of the function at the point m in the direction of x. Now, I can turn this around so that f is the given thing and x is the variable, and I then have a function from the tangent space to the reals. So xm is now the variable, and it maps across to a real number depending on the fixed function capital F, lowercase f, that I've chosen. And that's a linear map by properties that we saw much earlier, and therefore it's an element of the dual space, the dual vector space to the tangent space at little m. Now, we'll use the natural notation for dual spaces, put in an upper star on the T. This is the cotangent space of the manifold at the point little m, and this map from tangent vectors at m to reals is denoted by d little m of f. Of course, it's related to something we saw earlier. I'll come back and talk about that a little bit later. And it's easy to see that every element of the cotangent space at that point is dmf for some particular f, smooth function on the manifold. So we've got the dual space in a very concrete form. The dual space to the tangent space is these df expressions, or d sub m f expressions, determined by functions on the manifold. I now want to put a manifold structure on the union of all the cotangent spaces. And in a similar fashion to what happened with the tangent bundle, I think it's quite sufficient to simply say that we're taking the union of all the t star m, little m, to the manifold m. But if you want to be particularly careful, then you can attach the point m to t star of m at little m. I'll write omega often for elements of the cotangent spaces. That's to avoid specifying a function f when it isn't needed. But each element of this union is associated with a particular point of m that's built into the definition in the same way as happened with tangent vectors. And I'll write C for the map that sends a cotangent vector to the point at which it's defined. Okay, so now we need charts. Start off with a chart for m, and from that get the chart phi tilde for the tangent bundle. So that's a chart defined on TUM, where TUM, remember, is the union of all the tangent spaces at points of u, and the chart goes across to phi u cross Rn, which is an open subset of R2n. Okay. And I manipulate this phi tilde in order to turn it into a chart for the cotangent bundle. So notice if I fix a point of the base manifold of M itself and just look at phi tilde defined on the tangent space at little m, then I get a linear isomorphism to Rn, an isomorphism of vector spaces from the tangent space at M to Rn. And I can dualize that. And to cut down on notation, I'm just going to temporarily denote that by psi m. This is the dual map for, where are we? I haven't actually written it down, have I? The restriction here is, of course, phi tilde of m. Okay, and psi of m is the dual of this map, phi tilde restricted to the point little m. Now here, I've got the domain as Rn, and what I'm doing there is simply identifying the dual of Rn with Rn itself in the usual way using the dot product. Okay. So I can now take the inverse of psi m, and I've got a map from the cotangent space at m to Rn. And all I need to do is build these together, take them together over the subset U, and that will define me a chart phi bar, taking values in phi U cross Rn. And here's the formula, phi bar of omega, where omega is at point little m of the manifold, goes across to phi m, and then the inverse of the dual of the map that's defined by the chart for Tm at the point little m. It's rather awkward to say, and it's rather cumbersome to write down in detail, but the basic idea is very straightforward. You take the charts for Tm and you dualize them at it point by point on the base manifold, and that gives you a bijection, and you can look at the overlap maps. That's the next step. Look at the overlap maps for these charts, and they will turn out to be diffeomorphisms of open subsets of Rn. And I leave that to you to do, and of course you can ask if you get stuck, but in fact, I think you'll find it straightforward. Okay, so the psi, just remember, was a temporary notation just to cut down on the number of symbols on the page. That's the manifold structure on the cotangent bundle. It's a 2n dimensional manifold, and there's the map C is, where are we? The map C from the cotangent bundle down to M is smooth. Now, a differential one form on M is a smooth map from M into the cotangent bundle, such that at each point omega m actually lies in the cotangent space at that point M. So it's very similar to the definition of a vector field on a manifold. And the notation will follow the same conventions. The value of a one form at a point is just denoted in the ordinary functional notation omega brackets m. An individual cotangent vector at a point little m will generally denote by omega sub m. Okay. This is, again, it's important to distinguish between a single cotangent vector at a single point and a differential one form, which is defined on the whole of a manifold, or possibly a submanifold, but we'll deal with that sort of situation later on. Now, one forms, and by the way, I'll often just say one form rather than differential one form. One forms can be added pointwise, similar to adding vector fields. One forms can be multiplied by smooth functions, again pointwise. The set of all one forms is denoted by capital omega, 1m, and it's a module over the algebra of smooth functions. That's with respect to the addition here and the scalar multiplication there. And similar comments apply. There's always a 0-1 form. Not very interesting, but it always does exist. And more usefully, if I'm given a point m0 in the manifold and a covector omega m0 in the cotangent space at m0, then there exists a one form which takes that value, so that omega evaluated at m0 is the given cotangent vector. So there are a great many one forms, and in fact omega 1m is finitely generated and projective, just like the module of vector fields over the smooth functions. We'll come to that much later on. Now, the one form's been defined as a map from the manifold M into the cotangent bundle, but in fact, in practice, it's almost always defined in terms of its effect on tangent vectors or indeed on vector fields. And this presents a small notational problem. Let's deal with this first of all. Given a cotangent vector, that's just at a particular point, and a tangent vector, again at a particular point, I'll usually write the pairing, that's the pairing of a vector space with its dual, like that, using the sharp angle brackets. Okay. That's the pairing of omega m, which is an element of the dual space, to the tangent space, with xm, an element of the tangent space. And this notation has the advantage that it's symmetric. After all, the tangent space is the dual of the cotangent space, and there are situations where it's useful to write this pairing the other way round, and that's perfectly legitimate. Okay, and that reserves the notation omega m for the value of a one form at a particular point of the manifold. Now here's the proposition that we use repeatedly to define specific one forms. So suppose I've got a map lambda from the tangent bundle to the real, smooth of course, such that whenever it's restricted to an individual tangent space, it's a linear map. Then there's a unique one form omega on M such that lambda is in effect omega. Lambda applied to a tangent vector is the same thing as pairing omega at that point with x. So as I said, this is the way in which specific one forms are usually defined. And this is treating them as maps on the tangent bundle, which is a slight reformulation of the idea of them as maps from the manifold into the cotangent bundle. Okay. So, particular case, take a function on the whole of the manifold and define a map from Tm into the reals by sending each tangent vector to its evaluation on the function f. This is linear on each fibre, and therefore, by the proposition, it defines a one form which will denote df. Okay. And this df is the differential of the function f. And of course, at a point M is what we meant earlier by dmf. Now, I'm sure you've spotted that this map here is in actual fact the tangent map for f, except that I haven't kept track of the base point. So the tangent map would really go into M cross R. But this is simply the R component of it. And I'll talk much later about these 2 points of view, but it is useful to keep separate the idea of the tangent of a smooth function f and the differential of f. They're very closely related, but they're not quite the same thing. Final note, every cotangent vector that's at a particular point is dmf for some smooth function f. But it's not true, in general, it's not true that every one form is df for some function f on the manifold. And I'll talk about examples of that in the live session. It's true for some manifolds, not true for others. So the concept of pairing of a cotangent vector and a tangent vector extends to one-forms of vector fields. If you do this point by point, then you get a smooth function on the manifold. And I'll almost always use the sharp angle brackets for that. But in the literature, and sometimes in this course too, you'll often see that written as omega x. So you will have realized by now that there's a lot of abuse of notation going on. And generally, one abuses notation in order to keep things simple. It requires a little bit of extra thought sometimes, but generally speaking, it's something that's one can get used to fairly quickly. But there are situations where it's important to keep distinctions. So I'll normally use this notation, and as I said a moment ago, it emphasizes that the pairing is a symmetric thing. The tangent bundle is the dual of the cotangent bundle, and therefore one can sometimes write x omega. Okay. Now here's a proposition that's important for several reasons. For any two functions f and g on the manifold, the differential of the product is given by this product rule. And I'll do the proof of this as an illustration. I'll apply both sides to a function, to a vector field rather, on the manifold. In fact, we've got here a one form and a vector field, and I'm looking at the pairing, and I know that that's equal to x of fg, and of course that's equal to f xg plus g xf, and I can write that as f applied to or multiplied by the pairing of dg with x, and then g, the pairing of df with x. And I can take these functions inside, because after all the pairing is defined pointwise, point by point over the base manifold. So all I'm doing here is taking the scalar inside the bilinear pairing on the tangent and cotangent spaces. So finally, we have, I'm running out of space here, let's do it down below, FDG plus GDF paired with X, and that's true for all X vector fields on M. Okay, so the proposition follows. We'll see later on that every one form can be written as a finite sum of GDFs. So I said a minute or two ago that not every one form is a DF. True for some manifolds, not true for others. But it is true that if you multiply your DFs by G and allow finite sums, then every one form can be written that way. But it's certainly not unique. In fact, the proposition just shows that it's very definitely not unique. And by the way, this is roughly equivalent to saying that the module of one forms is finitely generated and projective. So finally in this podcast, consider a chart on the manifold M, call it phi as usual, and write x upper 1, x upper n for the coordinate system that's introduced by the chart. Now these are functions defined on an open subset of M, and they therefore induce one forms defined on U. We can take the differentials of local functions. And we also know, of course, that the chart introduces the local vector fields written partial 1 to partial n. And it's then almost immediate that if you pair the dxi with partials, actually that's dxj, isn't it, with partial I, then you're essentially just partial differentiating xj with respect to xi, and that's Kronecker delta ij. So in fact, these dxi, these differentials of the coordinate functions, form the dual basis to the partial derivatives induced by the coordinate system. And we can write for any function f on M, we have at points of U, of course, this formula here, which is our notation for what would be written on Rn, like this. Okay, and the partial IF here is an abbreviation for differentiating f transferred to an open subset of Rn with respect to the I've coordinate function there. So to sum up, the cotangent bundle is a very concrete object. It consists basically of derivatives of functions, differentials, of functions, and there's a natural pairing of differentials of functions with tangent vectors, which is in fact the pairing of the tangent space with its dual. And this enables us to work with the classical apparatus of advanced calculus very efficiently. Okay, so that's all for now.